let me start from number 16 first. Follow the order. Number 16 actually not very hard. Here I just give you some basic information. This question I want to check your understanding, or if you know that counting method, right? Counting by reference method. So I want to practice that counting by reference method. Let me, it's fine. All right. So we practice counting by reference, okay? This method. Now we need to count the number of additions, right? We know each addition associates with a plus sign, okay? Now we want to count the number of plus signs. All right. The plus signs, the first one, we know the first one we can skip. So the first plus sign is associated with the first subscript. Second one, second subscript, and so on. Okay? And so on. Like that. 1-to-1 correspondence. Right? Then let us list all these subscripts: 7, 10, 13, ... Last one, 1,129. All right. Now you need to count how many numbers here. Okay? Count, but to count it, here I give you the numbers, not consecutive integers. So in our class we use consecutive integers. So the counting is very easy. So but here you need to find a way to count these integers in the set, in a convenient way, right? So you need to find a rule representing all these numbers. Can you see that rule? So here, so you can see the difference between two adjacent numbers. 3, right? Same constant number. So can you write out? Oh, 4. Oh, sorry. Yes, 3, right? 3. Okay, all right. So here you can see. Can you find the formula? So what formula? To cover all the subscripts. Right? You need to find that formula. So with that formula, then when you do the counting, based on the information given in that formula, so you can find a convenient way to find the number of elements in the set. Okay? So that's the, basic information. 2 points. Counting by reference idea. Second, when you do the counting, you need to base on one important formula. Okay? Not too hard to see. Because the common difference is 3, right? So in this formula, the common difference is 3. So you can figure out this formula easily. So that's number 16. Number 17, you need to find both minimum, you need to find, the minimum number, but you need to find both maximum and minimum. Yeah. So for this question, I give you some important steps. Yeah. Chuck, just join us. All right. All right. Yeah. So these points, yeah, pay attention to these points. Okay. All right. The first thing, basic formula. Yeah. We learned a basic formula. So you need to know that formula first. Okay. So this formula given, you can find it in module 1, part D. Okay? Yeah. So for that formula, remember, we can find both maximum minimum. So given n elements, yeah, total n elements, we find both maximum, minimum, we have a formula. Remember, we spent a lot of time to derive that formula, right? Yeah. So here, let me write it out. It's a general formula, remember? Even odd. Then, finally, we figure out a unified formula covering both cases. All right. 3n over 2 minus 2. So that's the basic formula. First thing, you need to know this. Yeah. Second, but you cannot apply it directly. Yeah. So here, I changed the condition. So you need to apply this formula in the right way. Yeah. Because we have the condition. This is the condition. Yeah. This is the condition. You need to, consider. You need to consider. All right. Yeah. So then, for this extra condition, so definitely you need to do some change. Yeah. You cannot apply the formula directly. You need to make some change related to this condition. Yeah. So one way you can do like this. Yeah. One way you can do like this. Yeah. Yeah. So in problem solving, actually this method is very effective. So here, let me introduce this method, because later we need to use this method many, many times. Yeah. The first step, remember last time in last lecture I mentioned one important problem solving strategy. This past Monday in that class I talked about one strategy. Here we can use that strategy. So what's that strategy? We can modify the given problem slightly to make it easier. That strategy. We can modify the given problem. So here, how to modify? Modify to make it easier. All right? How to modify? Remove the given condition, or we just temporarily ignore the given condition. Okay? Yeah. The condition. That's the modified version, right? Yeah. That's the modified. So we ignore temporary ignore this condition. Later we can add it back, right? Temporarily ignore this condition, right? Yeah. Because after you ignore the condition, you can apply the basic formula, right? Yeah. Apply the basic formula directly. Yeah. Because, that's the perfect situation we can apply that formula. All right. Then step 3, you need to add the condition back. Okay, bring it back. Bring the condition back. Yeah, because finally, you need to solve the original problem without modification. That problem-solving strategy, right? We learned in our Monday's class. Yeah. All right. To bring it back, then you can see after we add this condition back, you need to consider the question: how many comparisons can we save? Okay, yeah, that idea. Yeah. Because without given condition, we do certain number of comparisons, right? But with given condition, some of the comparisons can be saved. Think in that way. Yeah, yeah, because the given condition actually does those comparisons. Okay, yeah. So you can think in this way: the given condition covers some of the comparisons, right? And this part these comparisons can be saved. Then you need to minus that number of comparisons. So you can save. Yeah. That's the idea, these 3 steps. Okay? Yeah. Number 17. Yeah. All right. Yeah. I need to keep track of my time. Yeah. Because I may forget my time, so I need to. Sorry. I need to set alarm clock. Set my stopwatch. Yeah. Let me see how many. Stopwatch timer. Set my timer. Let me see. Okay. Yeah. So I can keep track of my time. Yeah. All right. Yeah. So this idea, okay? Yeah. Actually, in this assignment, we have another related question. We can apply this idea. Let me point it out. Yeah. Yeah. All right. Yeah. Look at this question. Okay. Yeah. So it's, I need to cover it. This question, we can apply the same idea we used in question number 17. Okay? How to do that? Because I give you an extra condition. This is the extra condition. Okay? Not in place. Yeah. All right. The first step, still temporarily ignore this condition. Yeah. So that we can make this question a little easier. Yeah. Without this condition, so we answer this question, it should be easier. Okay? Yeah. All right. So the step 1, find the find the number of all possible, right? Or number of inversions without the given condition. We have formula. Yeah. Remember? Yeah. You can go back look at our notes. Okay. So module 2. Module 2, part A. Okay. Yeah. Just a minute, not part A. Inversion. Inversion is in that, inversion is in that, bubble sort. Bubble sort, we talk about inversion. Okay? Yeah. So that's part. Yeah, anyway, so you can find the notes. Yeah. The bubble sort. Yeah. Yeah. So look at the notes of the bubble sort. We have that formula, right? Okay, all right, first step. The second step, you need to bring it back, the condition. Okay, when you bring it back, you need to modify. Oh yeah, but when you bring it back, so you need to do one more thing. Yeah, so here, let me add that. You need to do one more thing before you bring it back. Yeah. You need to answer one question. So the question, yeah, all right. So here, we know this number inversion. The formula we know, because the maximum number of inversion, we know that number corresponds to the worst case, right? Worst case. Worst case for sorting, right? Sorting, remember, when you have inversion, you need to do a swap operation. So the more swap operation you do, the slower, right? So that's why it's the worst case. Yeah. Yeah. So for the number of swaps. Yeah. So here you need to, that formula, okay? All right. The question is, you need to understand one piece of important information. So that is under what input we have this worst case, right? So because this worst case occurs for some special input, right? Yeah. So you need to know that special input. So you need to, see it. You need to figure out for under what input you have the maximum number of swaps to do in the bubble sort. Yeah, let me write a few words. Under what input you need to do maximum number of swap ops in the bubble sort. Yeah, because that number related to inversions. So because some students may ask, why you always talk about number of swaps? Because swaps closely related to the inversions. Only when you have inversions, you need to do swaps, right? Otherwise, you don't need to do swap. So the number of swaps equals the number of inversions. All right? Yeah. So after you know that, then you can do step 2. Bring you know, that condition back, then modify your solution. Yeah, small modification. Yeah, yeah, because the condition. So here the situation is, this given condition may you may need to change the given input. Yeah. So this condition may cause some change in input. Okay? Yeah. Yeah. So when you bring it back, then because that corresponding input here, the input we're talking about here, so what's input? This input. That input we get here does not satisfy this condition. Yeah. Does not satisfy the given condition. Yeah. In order to satisfy the given condition, we need to make some change. Okay? You need to do small adjustment. Yeah. So in the step 2, yeah. So you do some small adjustment. Okay? Yeah. Then you get a final answer. That idea. Okay? Yeah. All right, next question. Number 21. Yeah. Number 21. Yeah. One common mistake. Here, let me point it out. Yeah, because when I did grading before, so many students did one big common mistake. Yeah, here, let me point it out. So when you work on it, try to avoid that common mistake. Yeah. 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 Based on my online class students, I estimate approximately half of the students made that big common mistake. So what's that common mistake? So here, let me write, avoid a big, so yeah, because that is very big common mistake. Okay, yeah, so what's that? What's that? Do not expand the polynomial before counting. Yeah, because many students expand the polynomial. Very messy. Very messy. Yeah. And the bad thing is, after the expansion, the counting number is very big. The counting number is extremely big, several thousands. Many students, give me the answer, several thousands after expansion. Yeah, too many. Yeah. So keep the structure. Okay? Yeah. Keep original structure. Do not change the original structure. Do not break it. Yeah. Because the original structure already the factorization. Remember, the more factorization we make, the fewer number of multiplication the factorization has done. All right? But when you do the expansion, what's that? When you do expansion, you undo the factorization. That's very bad. Factorization. You undo it. Yeah. That's the reason your answer is so big. Yeah, the first thing, never do that. All right. Second point in this question. Also, the second worst common mistake. This is the worst common mistake. The second mistake, yeah, just next to the first one, second worst common mistake. Many students forgot the Horner's rule. Yeah. Horner's rule. Yeah, many students, when they counted, they forgot the Horner's rule, forgot to use Horner's rule. Okay? In each parenthesis, remember, when you count the number of multiplications, in each parenthesis, inside each parenthesis, you need to apply Horner's rule. Okay? Yeah. So the second is, don't forget to apply the Horner's rule. Inside each parenthesis. Okay? Yeah. Inside each parenthesis. Yeah, that's second worst mistake you need to avoid. Third mistake. Okay? Third worst mistake. Also pretty common. Number 3. All right. After you complete, the calculation inside each parenthesis, then you need to do the last round multiplication. There are many, exponent operations, right? Exponential operations you need to do. But when you do, so when you work on those power functions, so here, when you work on power functions, on 3 power functions, right? You have 3 power functions. Yeah, 3 power functions. What is the right way to work? Yeah. All right. So the strategy here, let me tell you the strategy. Important the strategy. To make the most efficient calculation, the strategy is share the square. There are many square operations, right? Share the square operations as much as possible. Share square. Okay? Share the square operations as much as possible. So what do you mean share square operation? Let me give you an idea. Square operation. Yeah. Example. Okay. So here, let me give a simple example. Okay. Sharing square up. Example. Okay. Yeah. what do I mean? Yeah. Let me give you the simplest possible example of square sharing. Okay, all right. So U square times V square. Okay, yeah. All right. When you calculate that, the better way, you share square. Okay, so what's that? You put U times V inside square. So they share the same square. Okay? Do not do square up independently. Okay? Yeah? Because if you do square up independently, you need to do more multiplications. Think about. Because you need one multiplication here, one multiplication here, after that another one, right? So total 3. Okay? Yeah, total you have 3 multiplication, right? But when you do sharing, right? So one multiplication inside parentheses plus another one, covering both operands, UV, so your total 2. So you can do fewer number of multiplications. Yeah. Yeah. But because our situation here more complicated than the simple case, but you just try to, work based on this direction. Okay? Based on this direction. How do you maximize square sharing? Maximize square sharing. Yeah. So then, after you follow these 3 steps, you can find the best solution. Okay? Yeah. All right. So that's this question. Oh, let me see. Yeah, I used too much time. Yeah. I think I have to stop right here. Okay? Yeah. So I need to, go back to our lecture notes. Yeah. So I have to stop at this point. Okay? All right? Yeah. So I explained 4 of the questions. Yeah. All right. And if you do not give me any more questions today, I only explain these 8 questions. Okay? I have 4 questions remain. If before the class ends, you still give me a few more questions, then I can include in my videos. Okay? All right. Yeah. Keep that in your mind. Yeah. So let me go back to our part B, the second topic in part B of module 3. I will also post this file. Okay. This annotation file. All right, part B. Yeah, so we were here last time. Okay, all right. Yeah, but at the beginning, I need to recall a little bit. Okay, so remind you our discussion. All right. Yeah, move down to the bottom. Move down here, right here. Okay, all right. Yeah. So at this point, yeah. Yeah. So let me connect my remote control. Okay. Yeah. All right. So at this point, remember, oh, I need to change my pen color. Our formula, yeah, so here, this formula, okay, this formula. Our formula is only true for the special case n is a power of 2. For the general case, it's not true. Yeah. Then, our goal, we want to move to the general case. But for the general case, so how do we go from a special case to the general case? Yeah. Then I mentioned another important strategy, problem-solving strategy in this situation. Yeah. So that strategy is, let me write here. We used it before, guess and verify. We guess it first. Then we verify it. Okay? All right. First, we need to make a good guess. Yeah. All right. So guessing step in problem solving is very important. Yeah. Actually, this strategy matches our real world experience. In your real world experience, many times when you need to solve a particular problem in your life, frequently you need to apply this guess and verify strategy. What's that? Yeah. Because when you get to somewhere, so you're not familiar with the environment, which direction you should go, usually you need to make a guess, right? Yeah, sometimes it's hard to figure out. Then, after you make this guess, then you need to see if it is correct. So you need to try a little bit. That's the verify step. If it's not correct, then you need to change. Make another guess. Things like that in your real life. Here we have the same situation. We need to make a guess. Yeah. So based on our real world situation, you can see the better guess you make, the faster you can get your final solution. If you think about, if you make a very bad guess, then you need to do many experiments, testing, checking, verifying, a lot of work in order to fix a very bad guess. If your guess is so good, very, very close to your final solution, then your fixing step very small. The amount of work you need to do in that fixing step very small. Here we have the same situation. Okay, all right. So we want to make a good guess, as good as possible. Yeah. So we base on the original formula. Okay. So the guess should be close to the original formula. As close as possible. All right. Then we find the problem in the original problem. This log expression, log expression may not be an integer. Yeah. So one thing we need to do, we need to convert it to an integer expression. Integer expression. Okay? All right. Yeah. Very natural way to go. Yeah. So regarding the integer direction from non-integer expression to integer expression, the easiest way to do floor function or ceiling function. Yeah. Two simple ways, floor function, ceiling functions. Two simple ways. Yeah. Round it down or round it up. Okay. Round it up. These two ways. Yeah. Round down or up. Okay. Yeah. But which way? Yeah. Here we have two directions to go, right? Yeah. So this time we narrow down our guess into two options. Okay, yeah. Two options, yeah. So that's much easier, yeah. So you can see our guess. The first option is we apply floor function. round it down. The second, round it up. Ceiling function. Both integer expressions. Yeah. Which one is correct? Which one we should choose as our final guess? Okay, a final guess. Yeah. Then we need to do experiments. We need to do, yeah. So our another strategy, we do testing with small input numbers, right? Yeah. So that's the verification, simple verification step. Yeah. We work on some very simple cases for our data. Yeah. So what simple case? Yeah. So let's consider n equals 3 case. N equals 3. Yeah. That's a small number. Yeah. Some students, if you argue, you know, n equals 1, simpler, right? But sometimes the simplest case may be too trivial. Now, remember, if some case too trivial, remember in our polynomial discussion, counting, number multiplication, if the experiments you work on too trivial, you cannot get helpful information, right? So when we choose the simple cases, we want to choose the simplest meaningful cases. Some cases, you know, doesn't help. Okay? Yeah. Sometimes the simplest case doesn't help. Here we want some case that can help. Yeah. Here, when n equals 3, the binary representation, we know 1, 1, right? Yeah. If you write a binary representation of 3, that's 1, 1. 1, 1, you're counting 2 bits. Yeah. Number of bits, 2 bits. So your answer is 2. Yeah. Now, then you plug in these two formulas. Which one gives you 2? Okay, all right. Log base 2 of 3, we know 3, 1 point something, right? Yeah, because 3 greater than 2. So it's larger than 1. 1, but less than 2. Yeah, because 2 squared is 4. Yeah, so log base 2 of 4 equals 2. Now you have 3. Yeah. So 3 between 2 and 4, so it is a number 1 point something. 1 point something, you round it down, so this give you number 2. Yeah. But this rounded up, this you get a 3. Okay? Yeah. But we know the correct answer is 2. That means the first version is correct. So when we make a guess, we should choose the first version. Okay? The first version. So that's why this guess is the best guess. This is our best guess. Okay? All right. Next, we need to move to the verify step. Yeah? So we just finished the guess. Next step, we need to do the verification step. Okay? And the verification, we should do it rigorously. Do our verification rigorously. Okay? All right. Then we need to prove it. Yeah. So this formula. So here we have this formula, but we need to show this formula is correct for all positive n numbers. For all positive n numbers. Yeah. And we prove it rigorously. All right. So that proof. So there is a powerful method we can use to prove it. Okay. Yeah. So the proof, there is a powerful tool to prove it. Okay. Yeah. Apply one famous method in this situation, this kind of verification situation, mathematical induction. Induction. Okay, all right. Mathematical induction. This method. Okay, yeah. So you learn it in your discrete math. Yeah. So here you can see in this class, we use a lot of background from Math 3000, discrete math. Yeah. There is one whole chapter covering this mathematical induction topic. Okay? Yeah. Yeah. Pretty hard. Yeah. Pretty hard. Not that easy. Yeah. So here I need to apply mathematical induction to show this formula is correct for all positive integer n. Yeah. Yeah. Although I can do it, yeah, but you know, our time is very limited, so I want to skip it. Okay, I want to skip it. Yeah. Yeah, but later we have another question. We need to apply mathematical induction in part B. Part D, the last part D of module 3, when we need to verify the Fibonacci formula, we need to apply mathematical induction. Yeah. So I want to only show you once. Yeah. Yeah. Because in order to make the proof here, I need at least 20 minutes. Yeah. So that's too much time. So I want to save that. Yeah. So for this example, I skip mathematical induction proof. But in the end of this module, I may, yeah. So at this point, I still want to show you how to use mathematical induction to verify the formula. Yeah. But if at that time, if we do not have a lot of time, so then I may skip. Yeah. All right. So we complete this topic. Yeah. Let's start next topic. Yeah. Because next topic also very important. It directly related to our programming project number 2. Yeah. After our second topic, B.2, yeah, based on this topic, we need to do our programming project number 2. Yeah. So this weekend, I will assign project number 2. Yeah. Although there is overlap with project number 1, because we do not have a lot of time left in this semester. So I have to assign it. I have to use some overlap, yeah, to give you, approximately 1 month. Yeah, at least 4 weeks. 4 weeks for your second project. Yeah. So for that reason, yeah, we have to, do some assignments with overlap. Yeah. All right. Yeah. Let's look at the B.2 topic. Variable size reduction. Yeah. Problem 12, greatest common divisor. This topic. All right. Given 2 non-negative integers m and n. Yeah. So here, non-negative. Okay. Yeah. So including 0. Yeah. 0 included. But another important condition: not both 0. You cannot make both m and n 0. Yeah. Because in that special case, you will have some trouble. So you do not allow it. Yeah. All right. Then the question, find their greatest common divisor. So here we use the special function, GCD function. Yeah. GCD function on 2 non-negative integers, yeah, excluding the 0, 0 case. Yeah. 0 for the 0, 0 case, not defined. Okay? So when you consider this, GCD 0, 0, it is not defined. Okay? Yeah, not defined. Okay? Yeah. So remember in the last lecture, Monday's class, we define the value 0 factorial equals 1, right? Yeah. So this value, can be defined easily, right? Yeah. But for GCD, you cannot define it. no matter any value you assign it, you get problem. Okay, you cannot. You cannot assign any reasonable value to it. Yeah. Definitely not 0. You cannot assign. People tend to assign 0. No, you cannot. You cannot assign 0 to it. Okay, so you cannot assign any integer to it. Yeah. So yeah, think about it. So at some point, I may explain that. So why it cannot be defined. Yeah. All right. Now our goal, we need to find the value of the GCD function. Okay. Yeah. So it looks not too hard, right? Yeah. But there is important point in this algorithm. Yeah. Because use this one, we related to, remember the topic of this part B, variable size reduction, right? Yeah. So it's a good example for the, variable size reduction case, reduction. Yeah. Yeah. This topic. All right. Yeah. Now, let us consider the solution. Yeah. I think most of you had experience before solving, calculating GCD functions in your middle schools, right? Yeah. Here again, because it is a topic of middle school math. Yeah. Yeah. So let's recall. So our first solution, let us recall how did we solve this problem in our middle school experience. Okay, all right. All right, middle school procedure, let me record it step by step. Yeah. All right, step 1, find the prime factorization of m, the first integer variable m. Yeah. Here, yeah, when we talk about solutions, yeah, so we can only consider both positive integers. Yeah. Because if one is 0, then it's 0. Okay? If m 0 or n 0, then the answer trivial. It's 0. Okay? All right. Not 0. The other integer. Yeah, sorry. Yeah, not 0. Okay? Yeah. GCD of m 0 equals n. Okay? Yeah. Not 0. Sorry. Yeah. Because if you look at the greatest, this m is the greatest. 0 is not as big as m, right? Yeah. So, yeah. So n is the answer. It's trivial. It's trivial, right? It's trivial. So that's why we can ignore the trivial cases. Yeah. All right. Find the prime factorization of m. Yeah. Yeah. Prime factorization, remember, in our part B of module 1, I talked about the prime factorization, right? Yeah. I gave you the pseudocode, right? Yeah. So at that time, so I said I prepare for our project number 2. Yeah. So you need to write code, implement that prime factorization function. Yeah. All right. So that's step 1. Step 2, find the prime factorization of n. Yeah, step 2. Step 3, find all the common factors. Because after you get prime factorization from both parameters, then you can find common prime factors. Yeah. Yeah. Remember, in our part B of module 1, I talk about a standard factorization. That's the what do we call power prime power form, right? Yeah, yeah, some name. Yeah, yeah. So you have prime, you have power prime representation. Okay, yeah, form. Yeah. So we use that standard form. Yeah. So find all the common prime factors Then, last step, compute the product of all the common prime factors. Yeah, so that's our middle school procedure. Yeah. So with that, now you can see, First, let me show you a simple example to recall that. So although you know how to do it, but here I just recall a little bit. Okay, all right. So I use a simple example to show you these 4 steps. All right. So here, the most important step of this method is the prime factorization. So later we will discuss about this prime factorization. When we calculate GCD of 60 and 24, let's look at the prime factorization of 60. 2 squared times 3 times 5. That's our standard form, right? Remember? So we solve the prime base numbers in ascending order. So then, so each prime base number we need to give appropriate exponent numbers. So in that standard form. The second one, 24, we can get 2 cubed times 3. After that, so let's compare. If they have common prime base number, but we need to get the common factor part. 2 squared is a common factor of both numbers. And for 3, it is just 3. So 3, right? Right. Then we have 12. Okay. That's our middle school method, right? It looks pretty simple. Pretty simple. So the question is this a good algorithm? So definitely it is an algorithm, right? It is based on the prime factorization technique. Based on this technique. Rely on this technique. All right. The question, if you want to think about if it is a good one or bad one, you need to consider the question. Is the prime factorization let's treat it as a big operation. This operation is huge operation, not like multiplication, division. That operation, small, simple, but prime factorization, we can still treat it as one special operation, but it's a huge one. Right? Is the prime factorization op fast? Right? Because the whole algorithm rely on this special operation. If the prime factorization operation is very slow, then your whole algorithm is very slow, right? Because you need to apply prime factorization operation twice. Okay? So the answer, very slow for huge numbers, okay? Not for small numbers. The reason when we do here, because these numbers too small, okay? But can you think about for huge numbers, then the prime factorization operation is extremely small. How small it is? So here we have a few minutes before the break time, right? Several minutes before the break time. So let me use these a few minutes to explain how slow it is. Very slow, extremely slow. Okay, how slow? Super slow. Here I can give you some background information. regarding how slow it is. Yeah. When you do, the first thing is, here I'm talking about the huge numbers. How large do you mean huge, right here? How large? We need to get an idea, okay, how large the number is, okay, all right. Let me give you some simple idea in your mind how large these numbers are. All right, yeah. So think about numbers with thousands digits. Is that big? Several thousand digits. How about that? Yeah. Here I do not say millions of digits, right? Yeah. So thousands of digits. Yeah. That large, that level, thousands of digits. Yeah. So not millions, not billions here, right? Yeah, because even thousands of digits, it's already extremely slow. Yeah. How slow? Yeah, let me give you an idea. How slow you need to expect. Yeah. All right. Use your own computer. Yeah. Yeah. Because you can write your prime factorization algorithm, right? In our Module 1 Part B, we have that pseudocode of the function implementation algorithm. So we can write the program easily. Yeah. But when you apply your algorithm, your function on a huge number with thousands of digits, yeah, so not bits, let's say digits, yeah, thousands of bits, then you may need, yeah, let me give you, how much time you expect to find the answer. Yeah. Yeah. Many years. Yeah. That long. Many years. Okay? Even not a month. Yeah. Not a month. In years. Several years. That long. That long. Okay? Yeah. So to give you an idea, why prime factorization is so slow, yeah, extremely slow. Yeah. Because at old time, yeah, here some stories. Yeah, here I can talk about some stories, related to prime factorization question. Yeah. Many years ago, yeah, 10 something or 20, around 10 to 20 something years ago, yeah, some organization gave a prize, okay, gave prize to the university to find the largest prime in the world, okay, largest prime in the world. We know there are infinitely many primes numbers, right? Yeah. So there is a result. In the number theory, there is a result. There are infinitely many primes. There are infinitely many primes. Yeah. This result can be proved in ancient history. Okay? In ancient history, yeah. You may heard of famous Greek mathematician Euclid, right? Euclid, yeah. So we will talk about Euclid algorithm soon. Yeah, Euclid. Euclid, in his famous book, He wrote, book in several volumes. It contains the proof of this result. It's a very simple proof. There are infinite many primes. Yeah. Although people know there are infinite many primes, but which prime is the largest known prime, right? You need to know it, okay? It's not trivial. It's hard to determine if a large number is a prime or not, okay? Yeah. So what is people need to find the largest, prime. So that one organization give up some prize. As I remember, the prize, not too big. Yeah, the prize, something like $100,000. Yeah. The prize is not super big. Okay, yeah. To give a prize to the universities, labs, university labs, So if anyone can find the largest prime in some period, right? Some period. You need to give a period, okay? Several months, or in the current year, things like that. Then you can win this prize, okay? Yeah. Yeah. Then, so you can use any method, computing methods you can find. Yeah. So people use many computers in the world, through internet. Yeah, because people can, using the computer resource from the internet to do the calculation. Okay. Yeah. They share the computing work, in many people's computer in the world. Yeah. Thousands of computers, that many, in order to calculate the largest known prime number. Okay? So here I just let you know how hard it is. In order to determine a large integer if it's a prime number, because first thing you need to check if it is a prime, right? Yeah. So if it's not prime, you can do prime factorization. If it is a prime, then you cannot do your prime factorization. Basically gives you the same number, right? Yeah. Basically it gives you the same number, yeah, for a prime. Yeah. Yeah. So then, finally there is one lab won this prize. Yeah. Yeah. And they use several months to find that large number. Several months. Yeah. Within the limited time. Yeah. So now you can imagine how hard. So if your algorithm relies on that expensive operation, how can you use that algorithm, right? Yeah. You cannot use that algorithm. Yeah. So that means this one, when you work on the large numbers, this method basically useless. Okay? Yeah. Pretty much useless. We need to drop it. In other words, we have to consider a much better algorithm without relying on prime factorization. You do not need to do any prime factorization, but you can find GCD. So find GCD without prime factorization operation. That's the goal. Okay? So our next algorithm, second one, method 2, we need to look at how to find GCD without prime factorization. Okay? All right. So let's take a break. After you come back at 7 o'clock, let's look at our method number 2.